So on day 2 of proofs, here's a couple things for you to talk about with proofs, because this is where we're spending the rest of the unit. Essentially, we have today and one more class and then a review day. Review day will be, I believe, we'll have a quiz next class and then the following one. The next quiz that we're going to have, it's going to be basic stuff more. Just, I want to see where you're at with this before we move on. So plan next class on having a quiz at the beginning of the class. We'll go over questions and then take that quiz. That will give me a little bit of an idea real quick where you're at before we finish up for the unit and tell me what I need to review the following day. Okay? Then on the review day, we will have a harder quiz. I'm going to design it in a way kind of like the test so that you can pick certain things out of different categories to do. Again, I have to write all that, but that's how it's going to be. So for your identities and your proofs here, these are just some tips for you to look at if you get stuck. This is a good page to go back to. First, and most importantly, work only on one side of the equation. What that means is, remember I told you when to set up your proofs, you set up either going from the left-hand side to the right-hand side or from the right-hand side to the left-hand side. Do not try to make your sides meet in the middle. This is where you will go wrong if you try to do that. So pick one side to start with, turn it into the second side. Always choose the more complex side, if possible. It's always harder to go from the simple to the complex. You always want to start with your complex. Look for things that you can do algebraically. Things to remember to look for. Add your fractions by getting a common denominator. That is a big one. We hate fractions. Just plain and simple, we don't like them. This will be common. Anytime you have two fractions, you need to think about getting a common denominator and putting them together. You can factor. We're going to spend some time looking at factoring today with trig functions. You can multiply things out. That's your basic FOIL. Okay? You need to look for trig substitutions. That's your basic 8 identities. One thing that we can do, and I kind of pointed that out on question 2, is change everything to sines and cosines. If you change everything to sines and cosines, frequently you can get the right answer from doing that. Replace squared expressions with Pythagorean identities, and always, always, always keep looking at your answer as you go. That points you in the right direction and tells you what direction that you should be going in. All right? So we're going to do a couple of these together just to kind of practice and refresh our skills and see where we're at. And then we are going to go from there to do some extra practice on your own. Okay? So we're going to just talk about question 1 here. If I was to do a proof for this, remember your setup. So if you do nothing else, what do? Set up your left-hand side. And I picked the left-hand side because it is obviously the more complex one. And what am I aiming to turn this into? The right-hand side. So at the end, I'm going to get to -2 cotangent squared x, which is my right-hand side. Okay, this one definitely steps it up a notch here from what we did before. My first thought on this one, when you look at this, the first thing that usually you want to do is to make substitutions. However, what's the only thing you can substitute for in this one? Secant. And what do we typically substitute for secant? 1 over sine. Do you really want to deal, or 1 over cosine? Do you really want to deal with a 1 over cosine that's on the bottom of a fraction? No. Me neither. Makes things very ugly very, very fast. The second thing that I see in this one is how many fractions do I have? 2. How many fractions or parts are in my answer? 1. So, again, our favorite thing of all time, how do I take 2 fractions and make them into 1? Common denominator. All right. Remember, this is not difficult, actually, but these are whole pieces. They stay together. So if the first fraction has a 1 minus secant, what does the first fraction need from the other one? A 1 plus secant. If the first or the second fraction has a 1 plus secant, what does it need? A 1 minus secant. Now, The common denominator is now 1 plus secant, 1 minus secant. Rather than leave it that way, what should I do with it? Put it together. So let's work on the denominator. You do not have to show all of the multiplication here if you understand that you are getting here, when you multiply these together, there are a difference of squares, right? So if I FOIL those two things together here, 1 times 1 is going to give me 1. My outer terms are going to give me minus secant. My inner terms are going to give me plus secant. What are those going to do? Cancel. Then my last terms is secant times negative secant, which will give me minus what? Secant squared. Now, if you want to show the full multiplication of that, you may certainly do that. I am just saying you may skip that step if you can do that, personally. You may always show more work, but that is an appropriate thing if you're trying to show less work that you may skip. Now, the top of this, the top of each of these fractions, from the top of the first one, what do I have when I multiply 1 times what I'm multiplying by? 1 plus secant. What do I have on the second one? 1 minus secant. All right, I'm going to pause here. Any issues with where we're at right now? This looks really complicated, and it's going to go very quick from here. Any issues with that step? All right, what happens here? My secants cancel, and what do I get on the top? A 2. All right, that's as far as I can get with my algebra. After you do a bunch of algebra, what do we look for now? A replacement or a substitution. So refer back to your identities. Anything we can substitute here that looks like something in the problem. Tangent squared. Can I substitute tangent squared for 1 minus secant squared? It's not tangent squared. It's close though. What is it? Negative tangent squared. Okay? My identity over here says 1 plus tangent squared is equal to secant squared. If I wanted to say 1 minus secant squared, how do I have to manipulate that? I have to move secant to the left, which means I have to move tangent to the right, both by subtraction. So that's going to say 1 minus secant squared is equal to negative tangent squared. All right, so that means my next step here, I can replace 1 minus secant squared with negative tangent squared. Now we're getting there. If I'm looking at the answer here, I've got a 2 in it, I've got a negative in it. The only issue is I have a tangent squared and a fraction rather than a cotangent squared. So here's my question. Cotangent is defined as the what of tangent? Reciprocal. So if it's on the bottom, essentially here's how you are thinking about this. Take the 2 and the negative and pull them out front. What you would have left is 1 over tangent squared, right? What's 1 over tangent squared the same as? Cotangent squared. And that negative 2 is out front. You can show that step that I just showed. Okay? You don't have to show that step. If that step didn't make sense to you, what else could you do with your tangent squared there? I can replace tangent squared with cosine squared over sine squared. That's another way to show this. When I have double fractions, how do I handle them? Keep the top. What do I do at the bottom? Flip and multiply. Oh, I switched that, sorry. I did. That's sine squared over cosine squared. No wonder you're looking at me funny. I keep writing the wrong thing here. Sine squared over cosine squared. And then when I flip and multiply, it looks like this, which I can then switch into cotangent squared. Either way you want to do that is fine. One way is kind of like factoring. The other way is kind of like double fractions. Whichever way makes more sense. Now that question, that's a harder question right there. We are dealing with double fractions, complex fractions. We're dealing with common denominators. This would definitely be in the medium level at least, if not the hard. Okay? All right? I don't know. Maybe. We'll see. Not challenge. Hard, maybe. All right. Let's flip to the next page and do another one together. Actually, I'm going to have you try 2. On something like 3, what you see first is foiling out your secant x plus tangent x. So if I FOIL that out, it gives me secant squared plus 2 secant tangent plus tangent squared. Here's the first place that we're kind of seeing. One of the things from the checklist was turn everything into terms of sines and cosines. That's helpful to do here. Secant is the same as 1 over what? Secant's the same as 1 over cosine. So this one's cosine squared. This is 2 over 1 times 1 over cosine times sine over cosine, which we'll combine in a minute. Tangent is the same as what? Sine squared over cosine squared. If I simplify this middle part, it's going to turn into 2 sine x over cosine squared. Now, what do you notice about all 3 of your fractions here? They already have a common denominator. So that means I can make this 1 plus 2 sine x plus sine squared x over cosine squared. You could now factor from here, or you could make one more substitution. If I take out my cosine squared, could I make everything in terms of sine? Yes, and why would that be helpful to me? I'm going to the left-hand side, which is all in terms of what? Sine. So what can I replace cosine squared with? 1 minus sine squared. All right, and before I move on, I'm going to reverse the order on the top, too. Thank you. All right, so right now I have this. Any issues with that? Yeah.
I know you already explained it, but I'm just confused where you got, like, how you changed the middle term to 2 sine.
Okay. Secant here is the same as 1 over cosine. Tangent is the same as sine over cosine. So I multiply them together along with the 2, which goes on top. Okay?
Thank you.
Good question. Now, this is the first time we've seen this. So I want to point this out. This is actually something that you can factor. Okay, and here's how you have to see it. If you think about the sign as like the letter when you factor, that's in the same form as something like this. Can we all see how that looks similar to that? Saying that the sign is basically your y there. Okay, so how would I factor something like that if it was just y's? What would that factor into? Y plus 1, y plus 1, right? So instead of y's, I now have sines. So what's that going to factor into? Sine x plus 1, sine x plus 1. Now, yesterday or last class, we already factored something like the bottom. How can I factor 1 minus sine squared? 1 minus sine, 1 plus sine. Now, what does that do for me? It cancels that. Is that the same as the left-hand side? It is. The top is just in a reverse order. Does it matter? No. I can make that 1 plus sine, 1 minus sine, which is my right-hand side, or left-hand side, excuse me. Now, Lakey did it in a way that I hadn't thought of, and I just want to show you real quick because it saves a couple steps. You get to the same place here. But real quick, I want to show you that and then how you could go from the left-hand side. Rather than immediately going for foiling, and I've never seen it done this way quite yet, so I like this. Lakey immediately went to 1 over cosine and sine over cosine in here. I never thought about doing it this way. You have a common denominator there, which is 1 plus sine over cosine. And then she squared everything, which actually kind of cleans it up a little bit. If I FOIL out the top, it gives me 1 plus 2 sine x plus sine squared and cosine squared on the bottom. And then you finish it out the exact same way that you finished, but it saves you a bunch of steps in the middle. Why would you not FOIL? I did FOIL the top. Oh. Uh-huh. What do you mean?
Why would you not just do like 1 plus sine x times 1?
Oh, you could, yeah. That's a good idea too. I didn't even think about that. So you could, instead of FOILing out the top, you could leave it as 1 plus sine x, 1 plus sine x, since you recognize it. It's very similar to the top there. The bottom then is cosine squared, which you can then substitute 1 minus sine squared and factor that. Which would look like this, and then finishes the same way. But that does save quite a few steps, and honestly, I've done this for 3 years, and I've never seen that way yet. So I like to walk around and see what you do, because it's different. Real quick, if you want to see left-hand side. No? Not too difficult, actually. For those who want to, I'll show you real quick. When they're like this, what I can do on that one, if I want to simplify the bottom, I can multiply both the top and the bottom right here by 1 plus sine, which then I can FOIL the bottom together. FOILing the bottom together would give me 1 minus sine squared. I could FOIL the top together, which gives me 1, or I don't even have to. I see it better that way, but 1 plus 2 sine x plus sine squared. I can change the bottom to cosine squared and then divide each piece by cosine squared and then factor from there. But that gets kind of ugly. So there, 1 over cosine squared would be secant squared. 2 sine x over cosine squared would be that 2 secant tangent. Sine squared over cosine squared would be tangent squared, and then you can factor it into the original. It's a little harder to see that middle step when you divide. I like this way over here the best.
Could you do 1 minus sine x over 1 minus sine x and multiply it?
1 minus sine x and 1 minus sine x?
Or no, 1 minus sine x over 1 minus sine x. And then times that to the whole one.
You could. It might work that way too. Yeah.
Okay.
All right. So to use your double angle identities, I'm just going to give you an example to work on with this. So if you'll just find a blank spot in your notebook, I will give you an example, and we will use our double angle identities to prove it. So a good example of this is to prove this. Now, how would I know to use double angle identities with this? My tip-off is this 2 theta on the left. You can't get rid of a 2 when it's inside with the angle. It's not like you can just factor it out or divide by 2. Okay, so the minute you see a 2 theta or a 2x or 2 anything like that, you need to use your double angle identities. Which side would you prefer to start with on this one? I would probably start with the right. I can see more to do with that. Usually it's easier to FOIL something out than to factor something to make it look like that. So I'm going to go ahead and start with the right-hand side. What would you do first with this? We'd FOIL it out, making sure that that does not mean just distribute your squared. Okay? Please don't make that mistake. So that's going to give me, if I FOIL that, sine squared, because I'll do sine times sine. The outer terms will give me sine times cosine. The inner terms will also give me sine times cosine. What's that going to make when I put them together? 2 sine cosine. Then the last term will give me plus what? Cosine squared. All right, anyone recognize something in this that we can use to make a substitution? Okay, notice I have a sine squared plus a cosine squared. No, they're not sitting next to each other. Does that matter? No. What's sine squared plus cosine squared? 1. So now I have this. Go look at your double angle identities. Does that look anything like one of your double angle identities? This right here. 2 sine theta cosine theta, according to my double angle identities, is equal to what? Sine 2x, or 2 theta, which is my right-hand side. So it's just more tools to be used. It doesn't mean you do proofs differently. It just means there's some other patterns to look for. Okay? Any issues with that? All right. That is not on the quiz, no.